Hi, welcome to Veda Gate Academy. Now we discuss something about operational amplifier, right? Which is a part in the unlock circuits, right? So in the unlock circuit, this operational amplifier have a good weightage, in the gate exam. So operational amplifier is simply called as an op amp. So it is the first integrated chip element that can be used as an amplifier. Before this operational amplifier, I think that we are getting that design of amplifier using discrete component circuits with the help of a BJT or FET or MOSFET. So it is the first integrated chip element that can be used as an amplifier. And as compared to the BJT or FET or MOSFET amplifiers, this op amp can amplify AC as well as DC signals. It not only amplify AC, it can also amplify DC signal. By that, operational amplifier commonly classified as a DC amplifier. And based on that, its lower cutoff frequency, right, is equal to 0 hertz you can call. And it has a very high gain you can call. So it is having very high gain, and it is a direct coupled circuit. I think that small signal amplifiers uses capacitive coupling, large signal amplifiers uses transformer coupling, and this integrated chip body of operational amplifier uses direct coupling you can call. The mainstays in the case of operational amplifier is a differential amplifier. So this is the mainstays in the case of operational amplifier, that is differential amplifier you can call. So the name itself indicates that in the case of differential amplifier, the output can depend on the difference of the two input signals you applied. So the output not depend on the individual inputs. The output can depend on the difference of the two input signals that you can be applied at the input you can call. So now this is the differential amplifier you can say. So it can have the two input signals. So this is the differential amplifier now I can call, maintaining two inputs. Some V1 and V2 we can call. And whatever the output you say, that output can always depend on the difference of the two input signals, not on the individual inputs you can call. The difference of these two input signals is called as a differential input voltage. So denoted as VID you say. VID stands for differential input voltage. And it can be expressed by means of a gain. That gain is called as a open loop gain or differential gain you can call, A or AD. Okay. So the output V0 can always depend on the difference of the two input signals called as a differential input voltage. So under ideal condition, the output do not depend on the common signal to both inputs. The output can do not depend on the common signal to both inputs. The output 100% depend on only the difference of the two inputs. For ideal case, you can call. See, so now for ideal case, what I say means output purely depend on the difference of the two input signals only. So the output can depend on the difference of the two input signals only, not depend on the common signal I say. So now you can able to write this output V0 equal to AD VID or A VID you can call. AD or A is nothing but called as a open loop gain or a differential gain you can call. So this is for ideal condition. Suppose if you go for practical case, what you say means the output not only depend on the difference of the two input signals, the output not only depend on the difference of the two input signals, the output can also depend on the common mode signal to both inputs. So in the case of practical case, you can write like this. Suppose if I go for practical case, for practical case, you say that output V0 not only depend on the difference of the two inputs, but also depend on the common mode input to both things, so that you return the output as V0 equal to AD VID plus AC VC you say. So this is the practical condition. In the case of ideal condition, you don't expect any output by the common mode input, but here you can expect the output by the common mode input also. Practically the output mostly depend on the differential inputs, but somewhat also depend on the common mode input you can call. Where AC stands for, this one stands for what means common mode gain you say. AC stands for what means common mode gain, right? So it is common mode gain you can call. And what is that VC means? VC is a common input to both, a common signal to both inputs you say, and mathematically this VC should be equal to average of the two inputs. VC equal to what means average of the two inputs you can call V1 plus V2 by 2, where V1 and V2 are the input signals you say. So VC should be equal to the average of the two inputs. And you know that VAD is a differential input you can call. So that is nothing but difference of the signal voltages applied at the input. V2 minus V1 you can call. AD is nothing but already know. This is called as a differential gain. It is called differential or open loop gain you can call. Right. So this is the case of a practical condition. So when the op-amp come to the ideal case means of keeping this one to be negligible, under that condition the op-amp close to the ideal case you can call. Right, how much of the common mode signal that can be rejected or suppressed by an op-amp means that can be known by means of the one of the characteristic of an op-amp, that is called as a CMRR you can call. So CMRR is one of the characteristic of an op-amp using which one can identify how much of the common mode signal can be suppressed. So CMRR stands for what means common mode rejection ratio, that to be indicated by what means rho. Okay, so it is expressed as the ratio of differential gain to the common mode gain you can call. Right. So for ideal case, this common mode rejection ratio should be infinite. So that meaning that differential gain is infinite or common mode gain is 0. Means under ideal condition he say that any output by only differential and never by the common mode input you can call. Right. So now can able to examine the ideal characteristics of an op-amp. See, so now what are the ideal characteristics of an op-amp? Now I can check out ideal characteristics of op-amp. Now I go. Okay. So this is the op-amp symbolic representation. Right. So this is the output terminal V0. It have the two input signals, right? Those are V1, V2 you can call. And it uses two bias supplies that are called as a saturation voltages also, plus VCC and minus VCC you can say. Right. So this difference of these two signal inputs called as a differential voltage I can call. Right. And you see this one now, among the two inputs, one of the input is marked negative, other input is marked positive we can call. So this negative marked input to be called inverting input, that to be called inverting input you say, and one more is non-inverting input you can call. So this is the symbolic indication of op-amp you say. Okay. So what is the negative sign of this inverting terminal means that negative sign of the inverting terminal indicate a phase shift of 180 degree between output and inverting input. Always output and inverting input are opposite phase you can call. And what is the positive sign of the non-inverting input means it indicate output and non-inverting input are always in phase you say, right? The phase shift between output and non-inverting input is 0 degree you can call. And it uses two DC bias supplies that itself indicate the saturation voltages. One is positive VC plus VCC, other one is minus VCC you can call, and it is expressed by a gain that is open loop or differential gain you can call A or AD. Okay, so now we can able to examine the ideal characteristics of an op-amp. So first one of that one is what means the open loop or differential gain is infinite you can call. A or AD is infinite. So what the meaning of this one means, it indicating that in the case of an op-amp, the output is 100% only by differential input only, not by the common mode input you say. That's the meaning of it. So we can also say that the common mode gain AC tends to 0. So these things indicating that nothing you may get by the common mode input, right? No output by the common mode input signal you say, any output only by differential. These together indicated by CMRR, just now you checked out that CMRR rho tends to be infinite you can call. So CMRR should be infinite you say. And in the case of an op-amp, you remember that the bandwidth of the amplified output mainly depend on the slew rate you can call. So slew rate is one of the key person in the case of an op amp that can define the slope requirement for undisturbed output you can call. So for ideal case, the slew rate of the op amp should be infinite, right? So slew rate is infinite means it itself indicate that the bandwidth of the op amp should be infinite. For ideal condition, bandwidth is infinite you can call. What are the meaning of infinite bandwidth means? In the case of an op amp, right, we can able to get a good amplification for any signal, for a signal of any frequency, right? What are the signal of any frequency it can amplify faithfully without any distortion you can call. But in practical case, bandwidth just a high value, not be infinite you can call. So in the case of practical case, it have a good gain for DC signals, and the gain somewhat decreasing as the AC of frequency increases. Under ideal condition, it has high gain at all frequencies, that is considered without any attenuation. For practical case, bandwidth is a high means, right, it have a good gain for DC signals, and the gain somewhat decreasing as AC frequency increases you can call. So that's a bandwidth user. And one more key person here, input resistance is infinite. So where do you define the input resistance of an op amp means? The input resistance of an op amp always be measured between its inverting and non-inverting terminal, this one. So this is the place where you see that input resistance. So that input resistance of an op amp seems to be infinite you can call. So the input resistance is infinite means the input terminals look like to be open. So it is always be measured between inverting and non-inverting terminals that look like to be infinite you can call, indicating that the corresponding input terminals are left to open. So according to the ideal condition, none of the current can flow between input terminals, you say, right? So ideal condition, infinite input resistance. Practically, that input resistance would be very high, you can call order of mega ohms. So even in practical case also, right, the current flowing between the input terminals is negligible, that do not be considered. Okay, and one more is output resistance R naught tends to 0. So right, the output resistance of the op amp should be 0 you can call, indicating that all the amplified signal can be given to the output terminal without any loss, right? So for ideal condition, the output resistance should be 0 you say, indicating that all the amplified signal can come to the output without any loss you can call. So this will be the output resistance of an op amp. So all this will be the ideal characteristics for op amp you say. Let us see this one now. You can able to examine the transfer characteristic, that is output versus V0 versus VID characteristic of this op amp, that is not but a differential amplifier also you can call. So now I can able to sketch the transfer characteristic, that is V0 versus VID. So practically how it is you can able to check out. So this one now, transfer characteristic. So by this you can able to identify in which area the op amp can able to act as an amplifier and act as a switching device. So transfer characteristics now I can able to discuss. So that the transfer characteristics is nothing but drawn between output versus differential input voltage I can call. So this is that one now, sir. So this is VID, positive side. This is minus VID I can call, and this is V0. Now if I draw the transfer characteristic, that is nothing but output versus differential input, then the graph may come like this. Up to certain area, the graph look like a straight line, that is nothing but a linear you can call. After that, what you can expect means like this. So this is the transfer characteristic of the op amp circuit, right? It has some linearity portion for VID of certain area, and in the remaining condition, the output do not be responding, even the input voltage changing you can call. See, so now what are the indication of that? So this is the place where output varies linearly with the differential voltage you can call, right? So in this place, the op amp can able to act as a ohmic element, that is nothing but a linear device. So it is called as a linear region, you say. So this is the linear region of op-amp where the output can be amplified properly for the given input you can call. So in this linear region, the op-amp can able to find so many applications, right? Op-amp can be considered as a adder, subtractor like this, right? Op-amp is one of the building block element in analog computers, I think that you know. So majority of the op-amp applications should be expected in this linear region, right? By that, you know that any reference textbook of op-amp, it can be printed as what means linear integrated op-amp circuit. So the op-amp can find out the linear property in this area where output can be linearly varied with respect to the differential input you say. So practically this linear region should be considered in between the scale of plus or minus V2 you can call. So this is the scale where that linearity portion should be happen. So this is that one. This is minus VT. VT stands for thermal voltage, you know. This is plus VT can call. So total it is nothing but plus or minus VT. What is that VT? You know, VT stands for thermal voltage you can call. VT stands for thermal voltage. At room temperature it is how much means 26 millivolt, you know, at room temperature of 300 degree Kelvin, right? So once this linear region crossed, what happened means the op-amp can able to go for saturation mode you can call. In that saturation mode, the output do not respond even the input changes. So this is the saturation mode you can call, called as a positive saturation area. This is positive saturation and this is negative saturation you can call, where op-amp to be used as a switching device. So once the linearity region crossed, the op-amp can able to find the saturation mode where the output to be clamped at either positive saturation or negative saturation value you can call. What is that positive saturation means? That I told in the symbol, that is the saturation voltages. That is positive saturation means this is plus VCC you can call. This is plus VCC. So negative saturation means that is minus VCC you can say, right? So any amplification should be happen within the scale of plus VCC to minus VCC you can call. You don't expect the amplification above positive saturation and negative saturation you say. In this saturation mode, the op-amp to be used as a switching element. There you find the applications of op-amp like a comparator, schemic trigger, multi-vibrators, astable, monostable. So this type of applications of the op-amp to be identified in the saturation mode. When the op-amp go for saturation mode means whenever the corresponding differential input voltage is practically crossing plus or minus VT scale. So plus or minus VT scale you see now, VT means at room temperature 26 millivolt means plus or minus VT is nothing but an average, how much means this is plus or minus 0.026 volt you can call. So to keep the op-amp in linear region, you remember that the differential input voltage must be kept minimum, negligible. So the differential input voltage must be kept negligible. Under that condition, the op-amp can able to identify the linear region. But practically how it is possible, how to keep VAD to be negligible means that to be done with the help of virtual ground you can call. With the help of what means virtual ground, we can able to keep the op-amp in the linear mode you can call. Suppose if this linear region is crossed, then op-amp can able to go for saturation mode. In that saturation mode, the output will be clamped at either positive saturation of plus VCC or negative saturation of minus VCC, depending on VAD positive or negative you can call. Under saturation mode, if VAD is positive, the output is fixed at plus VCC. Under saturation mode, if VAD negative, then output is clamped or fixed at what? Minus VCC you can call. So to keep the op-amp in linear mode, you should maintain the differential input voltage must be negligible. And under practical condition, at room temperature, it should be within the range of this one. But how to keep this one, VAD to be within a small range like this means that to be done with the help of virtual ground. I think that you know, most of the op-amp applications we can discuss with the help of virtual ground. So now I can able to examine what is that virtual ground, right? So now the virtual ground concept I can consider. I can able to discuss that virtual ground. What is this virtual ground means? According to the virtual ground, he say that if one of the input terminal is at ground potential, then the other input terminal is also look like at the ground potential, even if some signal voltage is acting there. So even some signal voltage is acting there, it is also look like at a virtual ground. It is also look like at a ground you can call. That to be called as a virtual ground. So according to the virtual ground, what I say, if one of the input terminal is at a ground potential, then the other input terminal is also look like to be at a ground, even if some signal voltage is to be acting there. So for now, suppose I take the example of some inverting circuit. This is some inverting circuit we can call. How do you call this is an inverting circuit? Means there I keep that non-inverting terminal to be ground, and signal voltage I apply to only to the inverting. So I can keep that non-inverting terminal at ground, and what are the signal voltage I apply to only to the inverting node, like this. This is the differential voltage, VID. This is some resistance, say R1. This is the signal voltage I applied there, some VI. Okay, so now how to express that inverting voltage means the inverting voltage is nothing but the voltage at the inverting node to the ground. This is the inverting terminal. So at that inverting node to the ground, who are there means R1 and VA is there. And already you know that as compared to the input resistance of the op-amp, this R1, whatever it may be, it is negligible. Ideally, you know that input resistance of the op-amp should be infinity. No, practically it is very high. So as compared to the input resistance of the op-amp, this R1 considered to be negligible. Based on that, you commonly say that V1 close to VI. Right. And what is the non-inverting voltage means? Non-inverting terminal versus ground you can call. So between non-inverting to ground, nothing is there. So V2 equal to 0. So you see this one now in this circuit, non-inverting terminal is at the ground and inverting node is at the supply voltage. Then according to the virtual ground, I can say that this inverting voltage is also to be 0. I don't say VA equal to 0. I say that the voltage received at the inverting node to be 0. That's the virtual ground phenomenon. How it is possible now? Can able to examine. See for now, according to the ideal condition, V0 equal to A into VID, right? So VID equal to V0 by A, VID equal to what? V0 by A. And you know that A tends to infinity, according to the ideal condition. As A tends to infinity means, then 1 by A tends to 0. Right? That implies VID equal to V0 into 0 you can call. That is 0 volt. Right? Already you know that what is VID means. VID is a differential voltage. That is the voltage at non-inverting minus the voltage at inverting you can call. That is 0. Means V2 equal to V1. Right? So this is the case. V2 equal to V1 you can call. But according to the condition, you say now, suppose one of the case I taken, case 1 I check out as V1 equal to Vi, then V2 equal to Vi you say. First condition I say to keep that V2 equal to V1. As V1 equal to Vi, then V2 equal to Vi I say. So, but it is not possible because V2 is directly grounded, you can call. So, this statement is invalid, you say. This is invalid. Confirm now? So, as V1 equal to Vi, then V2 also equal to Vi, I say, but it is invalid statement. Why? Means V2 is directly grounded there. Now, I can able to check out. So, now I can able to check out case 2. Case 2 now I go as V2 equal to 0, as V2 equal to what I say? 0, then I say that V1 also 0. V2 equal to 0, then V1 equal to 0 to satisfy V2 equal to V1. So V2 0, then I may say that V1 also to be 0. Virtually in this circuit it is also not possible, but it to be possible by converting the open loop mode into the closed loop mode. So directly it is also not be happen there. So but it to be have a chance to be possible on converting the open loop circuit into the closed loop mode you can call. So in this case, what will I do means to satisfy this condition, I convert the circuit into closed loop mode now. I can convert the circuit into what's a closed loop mode now. See this one now? How to convert the circuit into closed loop mode means by connecting some feedback from output to the input you can call. So to which input you can apply the feedback means preferably you can apply the feedback to the inverting input. Why do you go for feedback to the inverting input means my requirement is, so originally V1 equal to Vi, that I wanted to decrease to become 0, not increase. I want to make that concerned inverting voltage from Vi to what means 0 I want. That to be done to decrease the voltage at the inverting node. How to decrease the voltage at the inverting node means by applying a negative feedback. So taking a feedback from output to inverting input look like a negative feedback. If I apply a feedback from output to non-inverting input means that look like a positive feedback you can call. So to reduce the voltage of this inverting node, you preferable to go for negative feedback, that to be obtained by taking a feedback connection from where to where, sir, means output to inverting input through some feedback element. That I do now. So open loop circuit virtual ground is impossible. That to be happen by converting the circuit into closed loop mode like this. So the effect of this feedback element RF such that the voltage received at the inverting input to become 0. So I don't say that VA is 0. The received value at the inverting node to become 0. That you remember, VA not be 0. So what are the voltage you received at the inverting node to become 0 with the effect of this feedback element who connected from output to inverting input. So with this one now, virtually whatever that V1 equal to Vi, now it can be decreasing with the effect of negative feedback and there is a chance to become to be 0. Once V1 to be 0, you know that VAD equal to V2 minus V1, that becomes 0. Then op-amp to be under linear mode. So we can able to keep that op-amp in the linear mode with the help of virtual ground, right? Virtual ground never happen in a open loop circuit. Virtual ground always possible only in a closed loop circuit. So according to the virtual ground condition, you see this one now. Here V2 0 means V1 to be 0. So what are that signal voltage not be 0? So what are the concerned inverting node to become 0? You can call. Suppose if I apply the feedback to the non-inverting input, what happen means then it look like a positive feedback. There mostly the op-amp enter the mode of saturation, right? So if I apply a feedback from output to non-inverting input means where VAD value may cross the scale of plus or minus VT now, automatically the op-amp may easily in the saturation mode, right? So in the positive feedback condition, you are giving a feedback from output to non-inverting input. Most of the cases there you can find the op-amp to be in the saturation mode you can call. So commonly you are giving the feedback to inverting input to say that the voltage at the received voltage of the inverting input to be decreasing and there is a chance to say that it becomes 0. By that V1 as V2 0, V1 becomes 0 you can call such that the op-amp is in closed loop mode you say. Let us see this one now, the condition of virtual ground. Two cases you say. Right, this is case of inverting amplifier condition. Two conditions I can show the virtual ground conditions. So this is inverting amplifier I call. In the case of inverting amplifier, you can apply the signal voltage only to the inverting terminal like this. Okay, these are the saturation voltages, VCC minus VCC you can call. So this is inverting terminal V1, non-inverting terminal V2, right? So now I can consider this one as a inverting amplifier. I consider that one as an inverting amplifier. There I keep this one to be at a ground. And I apply the signal voltage to the inverting node through some resistance R1. So this is the signal voltage I applied there, right? And I introduce a feedback from output to inverting input I can call. So it is a closed loop inverting amplifier also you can say. So this feedback element is nothing but RF I call. So according to the virtual ground, what I say means using virtual ground as V1 equal to 0, using virtual ground, what do you say? Using virtual ground, right, as V2 equal to 0 you say, then V1 should be 0 volt. So that op-amp should be in the linear mode. So this should be 0 volt you can call, right? So now I say that current flows here. I assume that the current coming here is nothing but some current I, and you know that input resistance of the op-amp is infinity now. none of the current can flow between the input terminals. Practically negligible current flows, that should be ignored. So that now I assume that the current in this feedback path is IF, right? So according to the condition there, you know I equal to IF. I is the current in the branch R1. One node is Vi, other node at virtual ground of 0 volt you can call, that is Vi minus 0 by R1. And this is nothing but 0, other node is V0, resistance is RF, you can call 0 minus V0 by RF. So implies output V0 is minus RF by R1 into Vi. So this is the output V0, that equal to minus RF by R1 into Vi there. So negative sign, what is the meaning of negative sign? Means negative sign indicate a phase shift of 180 degree between input and concerned output, you can call, right? So here the corresponding gain you say now, that is called closed loop gain also, you can say that I can call some A dash, that is called the closed loop gain, V0 by Vi you say, that equal to minus RF by R1. So we can able to get any gain just by changing this resistance values. That's the flexibility of this op amp circuit, you can call. So in the inverting circuit using virtual ground, V2 0 means V1 should be 0, you can call. This is the expression for the output of your inverting amplifier circuit, and the closed loop gain is nothing but minus RF by R1. There the lowest gain is 0, and you can able to get any gain just by changing or adjusting the values of RF and R1. So same circuit if it is non-inverting amplifier, how it means? So what is this signal voltage that can be changed to the non-inverting node, and here you can able to keep a ground. Just to check out that non-inverting amplifier. This is the non-inverting amplifier. These are the two amplifying circuits there. Suppose if we go for non-inverting amplifier, there we apply the signal voltage to the non-inverting terminal, and the inverting terminal commonly kept at the ground, you can call. See this one now? This is the non-inverting amplifier circuit. So this is the output V0, you know. So this is the inverting node. This is the non-inverting node, you can call. Okay. Now I can apply the signal voltage to the non-inverting terminal like this. You can apply either directly or through a resistor. That's no problem. Anyhow, that resistance is negligible in comparison with the input resistance of the op amp. So this is Vi call. Now I introduce a closed loop circuit through a voltage divider network. This is R1. Okay, this is RF. So this is the closed loop non-inverting amplifier circuit where signal voltage to be present at the non-inverting end, you can call. Let us see this one now. According to the virtual ground, here V2 equal to Vi means then V1 also equal to Vi. That's a virtual ground phenomena. So what are the non-inverting voltage should be reflected there. So here Vi is there, automatically inverting node voltage also Vi you say, right? This is the condition you say. Using virtual ground, right, as V2 equal to Vi, then you can also say that V1 should be equal to Vi. V1 equal to what, sir, means Vi you say. Now I indicate the current flows in this branch, some I say, and you know that negligible current flows or no current flows ideally, and now the current in this feedback path is IF, I can call. Again look like the inverting, here what you say means I equal to IF. So one node is 0, other node using virtual ground it is Vi, you can call, then 0 minus Vi by R1 you say, equal to IF, that is Vi minus V0 by RF. Right. So if I minimize this, I may get the expression for output is V0 equal to 1 plus RF by R1 into Vi. So output V0 equal to 1 plus RF by R1 into Vi, you can call. And whatever that closed loop gain you say, that expressed as some A dash. So that is output to original input, you can call V naught by Vi. Open loop gain means V naught by VID, you know. Closed loop gain means V naught by Vi, applied input. That equal to 1 plus Ri by R1. Right? Here, output and input are in phase, you say. In the previous case, output and input are opposite phase, but here they are in phase, you say. And as compared to the inverting circuit, there the lowest gain 0, here that lowest gain is 1. And if you select this ratio, RF to R1 ratio 0, then this circuit can act as a buffer, that we call as a voltage follower, you can call. So that mostly used in your digital circuit applications as a buffer. A buffer is one that can able to carry the input signal as it is to the output without any loss. So non-inverting amplifier circuit can act as a buffer, right? Taking that ratio, RF to R1 ratio to be as a 0, you can call. Okay, understand all this?